Hi, this is Shoikat Majumdar. Last day, or in our last video lecture, we have discussed the basics of the black body radiation. That is the introduction part of the black body radiation. The topic is same: Introduction to Quantum Mechanics. Learning objective is to acquire working knowledge of the quantum mechanics postulate on the physical system. Any heated body emits electromagnetic radiation. If the temperature of the body is increased, the wavelength of the emitted radiation decreases. Some laws related to the black body radiation. First, we will discuss Kirchhoff's law of heat radiation. The ratio of emissive power E lambda of a body to absorptive power for radiation of a given wavelength at a particular temperature is always constant. Mathematically, we can write E lambda by A lambda is a constant, say it is equal to K, where K is an arbitrary constant depending upon temperature. Now come to the construction of black body. For experimental purposes, a black body is made up by a hollow spherical copper enclosure with a small hole in its surface. This is the hole. This small hole is known as orifice. Inside of it is blackened by lamp black. Inside of it is blackened by lamp black. When any radiation enters the spherical cavity, it suffers multiple reflections at the inner surface. Characteristics of black body radiation. Number 1. Energy density only depends upon the temperature of the enclosure. Number 2. Radiations are isotropic and homogeneous in nature. Number 3. All bodies placed inside the enclosure also emit black body radiations. Comparison between thermal radiation and light rays. Thermal radiation and light rays both are electromagnetic waves. Number 1. Number 2. Radiant heat like light rays travel in straight line with the speed of light, and both can travel in vacuum. The speed of light is 3 into 10 to the power 8 meter per second. Both of them obey laws of reflection and refraction. Comparison between thermal radiation and light rays. Number 1. Thermal radiation and light rays both are electromagnetic and transverse waves. Number 2. Radiant heat like light rays travel in straight line with the speed of light, and both can travel in vacuum. Number 3. Both of them obey laws of reflection and refraction. Number 4. The wavelength of visible light, which is in the range of 400 nanometer to 800 nanometer, or in angstrom it is 4000 angstrom to 7800 angstrom, is smaller than that of thermal radiation. Energy distribution spectrum of black body. This is the energy distribution spectrum. In 1899, Lumar and Pringsheim, from the experimental result, obtained distribution of emissive power E lambda along this direction and wavelength lambda of black body radiation at different temperature. Observations of black body energy distribution spectrum. Number 1. For a particular temperature, the emissive power E lambda of a perfectly black body increases. For a particular temperature, emissive power E lambda is increases with an increase in wavelength. Wavelength is increasing and becomes maximum at this point. Here the wavelength is lambda m, maximum point at a particular wavelength. With the further increase in wavelength, if we increase the wavelength, the emissive power decreases. With the increase in wavelength, the emissive power decreases. Number 2. The maxima of the spectrum shifts from higher wavelength region towards the shorter wavelength region as the temperature increases. That means this is the maxima, this is another maximum, this is another maximum. The temperature is less, more. So maxima of the spectrum shifts from higher wavelength region, this is the higher wavelength region, towards the shorter wavelength region as the temperature increases. Just come back to the previous slide. This is the maxima, then shifting this, then shifting this, then shifting this. Lambda m represents the wavelength of maxima of a spectrum at temperature T. This is the distribution in terms of frequency. Here, if the locus is moving from this direction to this direction, here it is moving from this direction to this direction. So you can write lambda mt is equal to constant, where lambda m represents the wavelength of maxima of a spectrum at temperature T. For this one, so this is the lambda m here, and its corresponding temperature say 200 K. So lambda m into 200 is a constant. Wien's displacement law. As we see from the previous graph, lambda m corresponding the wavelength for maximum emission decreases with temperature. It was Wien who first discovered mathematically that lambda m is directly proportional to the temperature, or lambda m is equal to B by T, or B is called Wien's constant and its value is 2.898 into 10 to the power minus 3 meter Kelvin. The above law is known as Wien's displacement law. This is very important as it helps us to find the temperature of stars or hot bodies. Wien's displacement law may be expressed in terms of frequency as nu m is equal to Ct by B, as frequency is inversely proportional to the wavelength. Wien's distribution law. William Wien also used thermodynamics to show that the spectral energy density between lambda and lambda plus d lambda range is given by E lambda d lambda is equal to A by lambda to the power 5 function of lambda t d lambda. This function of lambda t can be expressed as e to the power minus small a by lambda t, where capital A is equal to 8 pi hc and small a is equal to hc by k. So we can write the equation E lambda d lambda is equal to A lambda to the power minus 5 e to the power minus small a by lambda t d lambda. So already we have discussed a and b are the capital A and small a are the constants. Wien's distribution law only can explain the shorter wavelength region of the blackbody radiation spectra. If we come to the previous, this is the shorter wavelength. This region is a shorter wavelength. It can explain only the shorter wavelength region. Higher wavelength region, it cannot explain. Rayleigh-Jeans law. Rayleigh-Jeans applied the classical law of equipartition of energy to this electromagnetic blackbody radiation. They found the energy density of radiation of wavelength lambda and lambda plus d lambda of a blackbody at temperature T is E lambda is equal to 8 pi kT by lambda to the power 4 d lambda. That means energy density E lambda is inversely proportional to the fourth power of its wavelength lambda. The energy density E lambda is increasing with a decrease in wavelength as it is inversely proportional with the wavelength. Rayleigh-Jeans considered few assumptions to overcome the failure of Wien's distribution law to explain the experimental result for a longer wavelength region. The assumptions are: number 1, the thermal radiation cavity is full of standing waves of electromagnetic radiations of all wavelengths. The walls of the cavity are perfectly reflecting. Number 2, the number of oscillators means mode of standing waves, per unit volume within the frequency range nu and nu plus d nu is given by n nu d nu is equal to 8 pi nu square by c cube d nu, where c is the velocity of light in vacuum. Number 3, average energy per degree of freedom of an entity can be written from Maxwell's law of equipartition of energy as E average is equal to half kT, where k represents Boltzmann constant whose value is 1.38 10 to the power minus 23 joule per Kelvin, and T is the absolute temperature of the system which contains the entity. Entity means harmonic oscillator, gas molecules, etc. Rayleigh-Jeans law can only explain the longer wavelength region of the blackbody radiation spectrum, where Wien's law can explain the shorter wavelength region of the blackbody radiation spectrum. Ultraviolet catastrophe. This is the energy density versus wavelength plot. Now from Rayleigh-Jeans law, we know the energy density E lambda d lambda is equal to 8 pi kT by lambda to the power 4 d lambda. Theoretically, if lambda tending to 0, E lambda tending to infinity. But experimental results shows the energy density decreases with the decrease in wavelength. That means in case lambda tending to 0, E lambda tending to 0. This discrepancy between the experimental and theoretical result of blackbody radiation spectrum at low wavelength is known as ultraviolet catastrophe. Look into this figure. This is the, as the wavelength decreases, This is the change. But as per theory, if lambda tending to 0, Rayleigh's law states that it will move to infinity. This is the ultraviolet catastrophe. But here in the curve, if lambda tending to 0, E lambda tending to 0 from this maxima to minima 0, it will not move to the infinity. This is the ultraviolet catastrophe. Stefan Boltzmann law. In 1879, Joseph Stefan and 1884, Boltzmann theoretically deduced a law relating the total power radiated per unit area of a black body to its absolute temperature. The law that they have given is known as Stefan Boltzmann law. Stefan Boltzmann law. In 1879, Joseph Stefan experimentally and 1884, Boltzmann theoretically deduced a law relating the total power radiated per unit area of a black body to its absolute temperature. As they have given the law, this law is known as Stefan Boltzmann law. Stefan Boltzmann law states that the total energy emitted per unit area per second from a perfect black body is directly proportional to the fourth power of its absolute temperature. Directly proportional to the fourth power of its absolute temperature. If it is directly proportional to temperature, we have taken a constant sigma. This sigma is known as Stefan's constant and its value is 5.672 10 to the power minus 5 arc per centimeter square per second per Kelvin to the power 4. In SI system, sigma is equal to 5.672 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. If a perfectly black body at temperature Tk is completely surrounded by an enclosure at T0 K, here T is greater than T0. That means temperature of the black body is greater than the temperature of the enclosure, surrounded enclosure. The amount of radiant energy per unit area per second can be represented as E is equal to sigma T to the power 4 minus T0 to the power 4. So this is all about Stefan Boltzmann law. Now, point to note, Stefan's law and Stefan Boltzmann's laws are not the same. Stefan's law is about single body heat radiation. However, the Stefan Boltzmann's law is about heat radiation exchange by the body with the surroundings. As per Stefan's law, the radiant energy emitted by a perfectly black body per unit area per second is directly proportional to the fourth power of its absolute temperature. E is directly proportional to T to the power 4. So E is equal to sigma T to the power 4, where sigma is known as Stefan Boltzmann's constant and its value is 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4. Now, heat H, the rate of emission of the body H is equal to E into A. E means sigma T to the power 4 multiplied by A, where A is the outer surface area. E represents heat radiation energy per unit time. T is the absolute temperature in Kelvin. Remember, whether the radiating body is hollow or solid, it is the outer surface area only which comes into the formula H is equal to sigma A T to the power 4. For non-black bodies, the heat radiated happens to be less, and for those bodies we write the equation H is equal to sigma E A T to the power 4, where E is known as emissivity or relative emittance, and the value of E is in between 0 to 1. E is greater than 0, less than 1, depending on the nature of the surface. Solar constant and the temperature of the sun. The amount of radiant energy received by the sun per unit area per unit time from the sun to the absence of atmosphere, on the absence of atmosphere when placed at right angles to the incident radiation at a distance equal to the mean distance of the earth from the sun is called solar constant, and it is represented by S. The measured value is approximately 1360 watt per meter square. The radiant energy emitted per second by the sun is H is equal to sigma area of the sun surface is 4 pi capital R square, where R is the radius of the sun, into T to the power 4. If the mean distance from the earth to the sun is smaller, then radiant power received per unit area is solar constant, and it is represented by S is equal to H by 4 pi small r square. So putting the value of capital H, sigma 4 pi capital R square to the power 4 by 4 pi R square is equal to capital R by small r whole square into sigma T to the power 4. This R by R is the mean angle subtended by the solar radius at the earth, and its ratio is 4.65 10 to the power minus 3 radian. Now what is the temperature of sun? So from this equation, H is equal to capital R by small r whole square sigma T to the power 4, we can get T is equal to small r square by capital R square into S by sigma whole to the power 1/4. Putting all the values, the temperature becomes 5800 Kelvin. This temperature is less than the actual surface temperature of the sun, because the sun is not a perfectly black body and some radiation is absorbed by the atmosphere.